Hello, today I'll be explaining quantum machine learning. My name's John Cook, I'm a machine learning engineer, and you can find my social media links in this link here, or you can use the QR code. There are a few types of quantum machine learning. There's quantum classifiers, which use quantum properties to classify data, and there's quantum annealers, which optimize traditional machine learning models using quantum techniques. There can also be a hybrid of the two types, or full quantum models. Today we'll be focusing mostly on quantum classification with supervised learning. The primary aim of quantum artificial intelligence is to improve human freedom, dignity, equality, security, and total well-being. Admit Ray. Why go quantum? If done right, it can train very quickly. It can have higher accuracy, and it can be parallelized across classes to improve performance. It produces comparable results with less computation in theory. Quantum machine learning can be very efficient, and it can do things a traditional computer or even supercomputer can't do if you have means to a powerful quantum computer. Pros and cons of quantum computing as it stands of today is you can perform complex calculations on a quantum machine that you couldn't on a traditional machine such as Shor's algorithm. This allows for faster and better calculations in theory. However, quantum computers are error-prone due to noise. They have limited capabilities at the moment due to the number of qubits. And for average users like me, you require a remote backend or a local simulation. How quantum classification works. Quantum classification works by representing the data in high-dimensional Hilbert space. It uses the special unitary group and its Lie algebras to manipulate the Hilbert space into a representation of the class, and then it continues to modify this representation until it matches the class closely, until it converges. Then it's compared to the actual label, and a prediction is made. Hilbert space is vector space that is very unique, but it has special properties that are ideal for machine learning. Lie algebra is something we use to manipulate the Hilbert space with the weights and biases. Lie algebra is very complex, but basically it's infinitesimals, or very small numbers, that are close to the center of the Hilbert space, and so they have greater control over how the Hilbert space ends up shaped. Quantum machine learning cycle is very straightforward. It's like a normal machine learning cycle. You have your forward step, but in this case we encode the data into a quantum state instead of just a normal vector state. We have the measurement state, or step, which measures the quantum state and makes a prediction, and then we have the backpropagation. Let's review some concepts. We have Hilbert space. It's high-dimensional space, perfect for machine learning. We have this special unitary group of n. N is the number of classes you have in this particular instance. And then you have your Lie algebra, which is used to manipulate the special unitary group and the Hilbert space to get the results you want. Now let's look at the code. Up here we have our imports. I need to clean it up a little bit, but it's just plain imports. Then we have our data preprocessing. We load the data. We don't do very much preprocessing, however we do sort the data, and I'll explain why in a moment. We then print out an image of 0 for the training or the development set, and make sure it's labeled as a 0, and it is. And then for the test data, we do the same. The 2 is a 2, it says, which is good. We then have an atom optimizer, which, if you're familiar with machine learning, it's probably the best optimizer available. That isn't quantum. And then we have our forward and backward step. This is where the meat of the code is. We have this H method, which is a generalized Hartman rate. In simple terms, it distributes the probabilities that each class is itself equally, so that you start on equal footing. This is done by entangling the qubits. And once you've done this, you can apply the weights and biases, but we'll get to that in a moment. Once you've done this, it's called a qunit, or a Q-unit. And once we have our Q-unit, we can apply the weights here. And we apply the biases up here. We use the Lie algebra and a term called alpha, which is what I'm calling biases. And it manipulates the Hilbert space, like I've said, and you get a result. This A term basically prepares the Lie algebra and the biases. We have a special unitary group of n, but in my code I had to use the special orthogonal group of n because it's very hard to calculate the special unitary group of n in high dimensions. It's easier to do the special orthogonal group as far as I can tell, but it's not as accurate. Then we have our Lie algebra, and I think my implementation of this might be wrong. It's kind of a hack, but it seems to be working to some degree. We then have our forward step, which ties all of that code above us together, and we get what's called a ket, or a vector of x. X is our data. Once we have our data in the quantum representation, we check the purity of it, make sure there's no errors. Generally there isn't, because I'm not running a true quantum system. And then we have our backward step, which takes the ket x and applies some calculations to it, a loss function, and then we just apply that in the training. Once we've trained, we then have our predictions, which basically runs the training but without the optimizer and a few other things. And after that, it doesn't take very long to run that bit of code, but once we get to the training, it takes 20 to 30 minutes for 3 iterations, which is pretty speedy considering the amount of data we have. Here we're just printing out 0 to make sure it's actually labeled correctly again, nothing went wrong. We then work on the Lie algebra, and for each class, and this is unique to my method or implementation, we have 0 saying it's 0 here in the training, which is a pretty small error rate compared to the other classes. And that's exactly what's unique, is that I print out how much it thinks 0 is the other classes, so if there's any confusion, you can find it. Now, it thinks that 0 looks the most like an 8 and then a 4, which you can kind of understand because 8 has essentially 2 zeros on top of each other. We then do a second iteration and then a third iteration, and then we move on to ones. And the unique thing about this class is that you sort your data, and then you run each class all at once instead of randomly one at a time, and this really speeds things up. And so we have our ones, and it thinks that 1 is 1 with a slightly higher error rate, and it continues. And like I said, this takes about Well, this time it was a little faster because I'm under less load, but it was about 20 minutes. We then get on to the predictions, and because the algebra is probably wrong and there's some other errors, these don't quite work. Like for 9, it thinks it's a 1. For this 6 here, it thinks it's a 0. So something's off. But I think I know what it is. I need to sum the classes, or the weights of the classes and the errors of the classes together before I make my predictions. And this should produce better results. I just haven't had time to implement it, and I'm not sure it will work, so I haven't gotten around to it. But that's pretty much it. If you have any questions, let me know. And thanks. You can find my GitHub here. My other links, such as LinkedIn stuff, are on this other link, and my email is right there. Thanks for coming, and if you have any questions, let me know.